Welcome back, ladies and gentlemen. So last time we learned about the stock naming system, basically filling in the whole center part of the periodic table. And we learned about this clever German guy who decided learning Latin was way too much work. So rather than try to call this cupric nitride, he just simply called it copper 2 nitride. Right? The 2 in this case meaning the charge on the copper. So this copper here would be, of course, 2 plus, as opposed to the nitrogen, which is 3 minus. 2 times 3 becomes 6, 3 times 2 becomes 6, which means this thing is balanced. And balance is what chemists always try to achieve. Everything wants to be balanced. Now you'd think, at this point, we've run out of periodic table to explore. After all, if I take this down, we have managed to find everything on the left and the right, and we just did everything in the middle. You might go, oh, well, there's this part at the bottom. We're not going to touch that. That stuff it's weird. We're not touching that. But what we are going to be dealing with is all the nonmetals up here. Because, as I mentioned early on, there are two different types of bonding that we're going to explore in this unit. We're going to be exploring ionic bonding, yes, but there's also something called covalent bonding. Now, we're not quite at covalent bonding yet, but there is still covalent bonding going on, and it still has an effect. Now, we're going to see more as we get into it, but basically what covalent bonding is going to do is it's like you and your friends all decide to go to the movies, and maybe you don't quite have enough money for each person to buy a ticket, but that's okay because your friend will spot you a little bit of cash. The problem is maybe you're still just a little bit short, just a tiny bit. So your group of friends can't quite make it in the door. Well, if only you had someone to donate a little extra money. Donate a little electron. What we're going to be talking about here is called polyatomics. Polyatomics. This word sounds pretty complicated, and it begins the long tradition that we're going to see over and over again of chemists being bad at naming things. So what they do is they change the name, the language, to a different one to make themselves sound smarter, but otherwise name it exactly what it is. So what we're going to deal with here is called polyatomic ions. Now, if we break down the word here, right, ion, we know what an ion is, right? That means something that's either positive or negative. Okay, so that hasn't changed. Atomic, well, we know what that is. That means like, atoms, pieces of matter. We're going to simplify it even more. Stuff, right? The stuff that makes up everything in the universe. Well, there's only this one thing in the front that we don't necessarily know what it means. Poly, what does that mean? Poly basically means many. So many stuff ions, many stuff positive and negative, or put another way, many atoms that make an ion. Oh, well, that's not so bad. Many atoms make an ion. Up until now, we've seen ions made with only one atom, right? Like I start with lithium with an electron on it, and then I turn it into lithium without the electron, and it's got a +1 charge. That is a single atom making an ion. Now we're going to make a bunch of atoms come together to make an ion. But how? How will we do that? What will we do? Well, it will make more sense as we learn about covalent compounds, but basically there are a series of compounds that involve all the nonmetals over here working together to try and buy that movie ticket, but not quite having enough. Let's take a look at an example here, because an example makes this a lot clearer. KNO3. We've seen compounds like this before when we were learning how to write formulas. We've also seen compounds where there have been multiple letters, but some of the letters were lowercase. All of these are uppercase, which means all of these are individual elements. Now, the thing is that everything up until now that we've dealt with has involved two elements, right? There's one on the left, one on the right, a metal and a non-metal. We've had copper oxide, we've had aluminum chloride, we've had all of these things, but they've all been 1 and 1. This is no longer 1 and 1, this is 1 and 2. Now, why am I grouping these guys together, kind of? 'Cause I know something you don't, at least so far. You're about to learn it yourself. This combination of non-metals, as I said, is like a group of friends going to the movies. They're working together to donate together so they can have enough money to get someplace, but they still don't have quite enough. But on the plus side, we know how much they need. We can figure that out. Why? Well, which one's the cation here? Right? It's the potassium. It's the first one. So that will be potassium. And then what's this guy? Well, you're in luck. Because while it doesn't follow a particular naming rule, right? We don't call that like nitrogen oxide or anything like that. Instead, we go back to our periodic table and we flip one more time, this time 2 pages in, to this wonderful page. And this wonderful page here lists all of the polyatomic ions that we are going to commonly work with. So if I want to name this thing, it's just potassium, and then I look it up. And I look for it in alphabetical order. So I look here, it starts with an N, so I go down the list, I find the N. Ah, here it is, nitrate. So this is potassium nitrate. And we're done. I mean, there's a charge here, and we could do the charge. We know how to do that because the potassium's always the same. It's always plus. And there's only one nitrate, which means it has to be minus. That's kind of it. They're more complicated because there are more pieces, but in terms of actually using them, it just comes down to looking stuff up. Let's try another one. Let's say I've got Na3PO4. Okay, once again, I have 3 elements here. I've got Na, I've got P, and I've got O. If I've got 3 or more elements, that means it's a polyatomic. I am no longer dealing with the first 2 examples that we did, and now I got to pull out my periodic table and take a quick look. If I look here under the P's, I will see that PO4 is phosphate. So in terms of naming this, this would be sodium phosphate. And that's it, sodium phosphate. Now, what's the charge? We have to be able to figure that out. And in order to do that, much as with the one previous, I could look this one up. Like I do have it here and I can look it up. But I can also do a little bit of detective work. I know what this guy is, right? Because he's always the same. Sodium's in the hydrogen family. It's in the alkaline metals. So this guy here has to be 1 plus. Plus. Well, there are 3 of them, which means that in total, this side is plus 3. That means this side over here has to be minus 3, because the 2 of them have to be equal to each other, right? Equal and opposite in order to cancel. Well, if there are 3 guys that are worth 1 each, and there's 1 guy, and they have to be equal, the 1 guy has to be worth 3 each. That way, they'll balance. Hopefully that makes a little bit of sense. Hopefully. But all right, let's try something a little bit more difficult. You're clever. Let's give it a go. We'll start off with the word. We're going to go backwards only. So I'll go with, let's say, beryllium nitrate. Beryllium nitrate. Okay. Well, beryllium, that's first. That must be a metal. So I will record good old Be. It's located right at the top of the alkaline earth family. So we got ourselves Be. Nitrate, why did I pick nitrate? Well, we already know what it is. It's right there on the board. It's NO3. So I'm going to put in NO3. Now, we have to make sure everything balances, though. So if we do the balancing, we're going to see this is going to be 2 plus, because beryllium's always 2 plus. And for nitrate, well, I can look that up on my handy chart here, but I also have it on the board. So it's negative. So this guy here is negative. So the beryllium is going to want to give away 2 electrons, right? They've got 2 electrons to hand out. The Nitrate is going to take only one. So I'm going to hand out two, but only one is going to go away. I've got one left over. Well, what's going to happen in that case? I need to give it to a second nitrate. And here's where something we learned when we were talking about the whole writing formulas comes back. I need two NO3s. So I'm going to put brackets and put a 2 down here, because there are two of everything in the bracket. I have to do it this way. I can't do this, right? A lot of people that want to do this because they're like, well, you know, whatever, I'll just do this. There's a pretty big difference between 2 NO3s and 32 oxygens. That's a huge difference. So you got to put those brackets in. And remember, we're doing subscripts because they're all connected together in some way, right? You know, the marker lid attaches onto the marker itself. So this one here won't cut it. No bueno. What does that mean? We've got to use those brackets again. Now, the brackets aren't going to always come up, right? It only really matters if I need multiple of these, but there it is, right? Like I didn't need it for this one. But at this point, you've now seen. So when you're trying to deal with these polyatomics, you're going to be taking the word for the polyatomic itself off of your periodic table because we don't expect you to memorize it. But otherwise, everything is pretty much the same. There's no real surprises here. All stuff that you already know how to do. It's just sort of building on the ideas you had before. The stock system introduced variability or differences in the metals. Polyatomics introduces variability or differences in the non-metals, in the anions. But otherwise, everything behaves the same. You're going to need to do some practice, though. Practice will always make this work a lot better. You'll find that there is quite a bit of practice. Get to that, and of course, ask questions if you're stuck, and I will see you next time.